So yeah, thanks a lot for asking me to talk in this Czech machine learning meetup. I have done a couple of French ones, a couple of in the US, but that's the first one, not in Czech, but for Czech people mostly. So really excited about that. So as Peter was mentioning, the first slide is a map. Where do I talk to you about? So we are not full lockdown anymore, but still working from home, I guess, as most of you. So the red point is where I usually work, south of Paris, in the Saclay, and the blue star, that is where I live. So that's where I'm right now. Just to give you that little town is not so little, 60,000 people. It's called Antony. So today we will be talking about supervised learning, and so I introduce it on this example of classifying pictures of cats from pictures of dogs. So human, even a very little human can easily do it, but how do we teach to a computer to take a database of pictures where we told which are cats and which are dogs, and then on a set of pictures that were not in the database, the computer should be saying correctly whether it is a cat or dog. So how does a computer see a picture of a cat or a dog? Or here it's some person because it's an eye, right? The computer sees a lot of pixels for 3 different colors, and the pictures encoded as a long sequence of 0 and 1s encoding the intensities of each of the color at each of the pixels. And then this task of supervised learning actually translates to taking this vector that here I call x mu. So mu will be index for different pictures. So if I have 1,000 of pictures, mu will be running from 1 to 1,000. And x for each of the picture is the vector representing the picture. There's this log sequence of 0s and 1s for the 3 different colors representing their intensities. And teaching a computer the rule of recognizing cat from a dog means mathematically finding a function that I call here f, such that if the function gets this long vector x as an input, it outputs +1 for a cat or -1 for a dog, or the other way around. So when you actually think about it like that, it looks less trivial. Like, how should I even go about writing that function and encoding it into a program? So indeed, it's not so simple as it is for us human. And say 20 years ago, we didn't know how to do that with computers. But these days we do, and it's all, you all have heard about it. It's because of this progress, largely from deep neural networks. So how do these deep neural networks work? How are they representing this function f? So before, the third point are the deep neural networks, but before explaining how that works, let me kind of bring you back maybe to your high school years, where you were in some physics experiments measuring dependence on something and fitting a line through the points. In that case, you were doing linear regression. Fitting a line is doing linear regression. Linear regression is the most basic tool in machine learning. And in terms of how I'm setting the problem, it corresponds to taking this function f as a scalar product between a vector of parameters, w, and the vector representing your data x in this case. And in high school, we were fitting a line. So in that case, the w just had 2 numbers, just had the onset and the slope of the line. And we could also do high dimensional linear regression when we would be fitting, when the number of parameters would be larger. But as long as the function f is just the scalar product of the parameters times the data, it's called linear regression. We could also talk about generalized regression, such as, for instance, logistic regression that many people working, say, in banking industry or finance or any kind of data industry use every day. Logistic regression is probably still the most used statistical method in the world. In that case, we still are just multiplying a vector of weights by the data as a scalar product, but we are, so that second line here, but we are applying some function on that product. For instance, the logistic function to get logistic regression, but in general any function, and that gives us a generalized linear regression. And now to get to neural network, it's again just a slight generalization of these ideas. So this time we don't have just one vector of parameters that we don't know, W, but we have several of them represented by these matrices here, W1, W2, W3. And we kind of take the output of the generalized linear regression and treat it as if this was the new data and plug it into a next layer of the network, meaning that we multiply it by a scalar product with a yet new set of parameters. And we do that many times, defining the width of that corresponding layer of the network, and that will be the first layer. And then we chain this several times, say 5 times or 4 times in my case here, and that defines the different layers of the neural network. So a neural network is just a fancy ansatz for this function that we are trying to fit on the data. And the width will be the kind of number of hidden units in each of the layers, and the number of layers is the depth. And if we have more than one layer or two in practice, people talk of deep neural network. Doesn't really need to be thousands, but it can be thousands in some of currently state of the art, it can be thousands. So it's a form, it's an ansatz for this function by which we are approximating this functional dependence from the input data to these labels. And so what do we do with these W's? So kind of general theory of learning is saying this is a good approximation. There exists a set of W's so that this fits nicely the functional dependence. But if there exists, it doesn't mean that we can actually find it with some algorithm that the computer can understand. So how is this done in practice? So the core of machine learning today is actually to take this function parameterized by all these W's and write some kind of a loss function, which is some kind of a distance between what the neural network is outputting for a given set of W's. And at the beginning, we are just starting with some random values. How is that output different from the desired output, these labels Y? So we define some kind of distance. This can be simply sum of square differences or some kind of cross entropy that is most often used in the current applications. And this is a loss function. We sum this distance up over all the examples, all the samples, all the pictures in the training data set that we had. And then we take one element of all these W's, compute a gradient with respect to that element. And we do that for all the elements. And then we change a little bit the W from those initial completely random values towards the direction of the gradient. And we go on this way. And this eventually converges somewhere. And if we do it for a long time enough by using a lot of CPUs, GPUs usually, and if we have enough examples in the training set, and if the training set is labeled and clean enough, and this learns a function that eventually is able to classify cats from dogs. So for cats and dogs, we also need to add convolutions, which is just a little bit of particular constraints on how these W's actually look like. But I will not be going into that. It's nothing particularly more complicated. So that's how it works. So the principle is really, really simple. We take this ansatz for the function and we do gradient descent with respect to the parameters. So what could possibly be simpler than that? It's very, very simple. So, and this is what leads to kind of all that engineering and empirical progress of machine learning, of deep learning that we have seen in the, say, past 10, 20 years. And we have seen a lot of that. And I am not even giving examples because all of you who came to this meetup must have seen dozens of them. So I think that would be just insulting your intelligence. So, but what I want to talk about today is, although the principle, kind of mathematical principle of what is done is simple because I just explained it to you in 10 minutes, do we actually understand why it works? And here, I come to the theory. And here I give you a snapshot of a paper that I have read something like a year ago that summarizes the 3 basic theoretical questions about learning with deep neural networks. And I will be going a bit more in detail to each of them. But what's really the most striking thing about this article is it's not from this year or last year or the year before, it's actually 25 years old. So it's from a note that statistician Leo Breiman wrote in 1995 about reflecting on a refereeing process for NIC. As it back then, these days it's called NeurIPS, that's the main conference of machine learning. And the striking thing is that these questions were there 20 years ago, and if you go to the theory section of NeurIPS this year or last year or next year, these are still pretty much the questions that people are discussing and that on which we don't have kind of a final answer. So what are, let me go through these three questions. So the first of them, so why don't heavily over-parameterized neural network overfit the data? So let me again remind kind of the basic concept of overfitting. So overfitting is the kind of when you fit, points by a line and you don't have, say, polynomial of high enough degree, but in this particular example is not polynomial of high enough degree, it's a neural network with enough hidden units, and these are ReLU hidden units. So if you just have very few, but it's really analogous to the degree of the polynomial about which you maybe have intuition from back your high school when you were doing these kind of fits and learning about them. So if the number of hidden units or number of parameters is too small, you don't have enough power to fit through the points. So that would be the first example here. Then in the middle, if the degree is just right, you kind of go through the points and also generalize well, because kind of all this function, the blue function, is close to the true red function. But then if you have too many of those parameters, then you go perfectly through the points, or almost perfectly through the points, but in between them where you don't have data, you do very badly. And this is what we don't want, because the new data that come to us on that where we want to test the method, they are somewhere in the space of the training data, but do not correspond exactly to the training data. So they're somewhere in between, and we want the result to be good for that. And then, so as the number of parameters is growing, you have this kind of trade-off between lowering the error. You need the model to be complex enough. You need the function to be complex enough to capture the dependency in the data, but not too complex so that it perfectly fits the data and actually hurts the generalization property, goes away from the red curve where there are no data. So that's kind of the common, knowledge. The interesting thing is that neural networks are completely defying this knowledge. So here I am showing you the full plot actually from a paper of my colleagues Andrew Saclay and Madhu Advani, where they also show a fourth panel. When you actually take way more parameters than kind of you need to be in the sweet spot, in this case 500 hidden units, you are back in the case where you actually pretty perfectly fit through the points, but also have a good generalization error. And this turns out to be a very generic property of neural networks, that even having much more parameters than even the number of examples on which you are training, there is something that implicitly regularizes the whole thing and lets you have a good generalization error, despite the kind of huge number of parameters. So this property has been kind of in the theory literature recently coined as the double descent property. And in the theory literature, there is the paper from which comes this picture by Misha Belkin and his collaborators. So he's a very well-known statistician, where he describes this kind of typical trade-off where the error goes down and then back up, but then it goes down again. And how did Breiman knew about this in 1995? Well, actually in the very classical paper where this bias variance trade-off was described, that comes from 92, this has already been observed. They have an experiment with a very simple neural network showing that the very concept for which this paper became very well known actually does not hold for a neural network. And that's the, that's just the picture from that paper. So that's how Breiman knew it. It was puzzling theoreticians already back then. So the second question about why doesn't backpropagation head to true local minima? Or third here, but I talk about it a second. So backpropagation is just the name of the algorithm of the gradient descent of the loss function, with basically kind of a smart bookkeeping of how the gradient is computing so that it's done sufficiently fast. But conceptually, it's the gradient descent. So the loss function is actually a very complicated function, depends on many parameters. These functions, these activation functions are nonlinear. This renders the function highly non-convex. So this is a highly non-convex, high dimensional function. So it should have in a priori many local minima, and something as simple as gradient descent should just get immediately stuck. But it doesn't. It's in practice, it finds something pretty good. So in the theoretical literature, one kind of line of work, a pretty popular line of work, is actually to show that there is something in deep neural networks that makes this function actually simple, that there are no bad local minima. And so people are proving under different unrealistic, of course, conditions that this function is actually simple. But more recently, there is a pretty strong empirical evidence that even in the state of the art neural networks, this function actually is not simple. One of the papers that I like that pretty nicely coins that difference is this one, where the title says it all. There are bad, even global minima, bad in the sense that the test error, the generalization error is bad, and the stochastic gradient descent can reach them. But if you initialize it randomly, it doesn't. And the reasons why this is so mathematically are still very obscure and nobody really knows. And this is bringing me to the question middle in the list of Braiman about what is the effective number of parameters, what is the effective kind of number of parameters, meaning what is the number of samples, this translates to what is the number of samples that we actually need to be able, a number of pictures, to be able to learn the function well. So here I'm just giving you a snapshot of the CIFAR-10 dataset that is very broadly used, especially in more like theory papers, to kind of illustrate simple concepts of how learning works. This dataset has 10 categories of different, airplane, automobile, bird, etc. For each category, there are 5,000 samples, so 5,000 images of each of these categories. And people would compete of who can get the best test error for this dataset. And people are doing, of course, well, and there is a broad literature about that. But nobody really knows is how many samples one really needs. You can, of course, try to reduce it and put less, and then your algorithm and your neural network architecture will do something. But nobody knows whether this is close to the minimum possible, or whether this is still way too much. And if it is way too much, whether this is because the algorithm could be improved, or whether the architecture of the network could be improved, or whether some combination of the two, or whether actually one would need to do it completely different. And these are very good questions, obviously. It would be nice to know, but we just have no clue. And kind of this is, of course, the question of sample complexity and how many samples we need to have a given error. That's the holy question in learning theory. And all the kind of 30 years or 40 years of work are asking the question. But there is this paper from some like 2-3 years back that is pretty much, putting aside a lot of the development in the theory literature by showing the simple thing that if you take your data set and you completely randomize the labels, you completely reshuffle the categories completely randomly, you can train your neural network still to 0 training error. Of course, the test error will be just randomly bad because your labels are random, but the train error can be 0. And okay, that's an empirically observed fact in that paper. But for those of you who actually know about learning theory and about what's the VC dimension and Rademacher complexity, etc., this is basically showing that 99% of the learning theory papers are good for nothing because they are relying on the fact that if the labels were random, you could not fit them perfectly. And because the networks are so over-parameterized, the state-of-the-art networks are so over-parameterized that they can even fit perfectly random labels, all these results are basically not useful, and we need a completely new learning theory, and we so far don't. So these are the questions. So what's kind of making the answer to these questions so complicated, and why nobody, there are many math and computer science people working on them, and what is maybe part of the reason why it's difficult to answer these questions. So I like to put it in this kind of a triangle. Actually, to understand the theory of deep learning, you crucially need to take into account the interplay of these kind of three sides of the triangle. So the structured data, the architecture of the network, and the algorithm. So let me kind of go through the three of them. Why cannot you understand things by dismissing one of these sides? So if you dismiss the algorithm and you're just asking kind of the approximability question, you will end up with results. Okay, if I parameterize the network, the function a given way corresponding to a given architecture of a neural network, then you may prove that there exists a set of parameters so that the approximation is good. But these are high dimensional objects, and if you actually don't have an algorithm that can tractably find them, that you may be ending with a completely algorithmically untractable problem. And that if you have million of parameters and the algorithm takes exponentially in that million, then this is useless. So you need to keep in mind that you need to be able to find those parameters fast, and that you cannot dismiss the algorithmic side. On the architecture side, that's pretty much the kind of current empirical evidence that there is something very good about these architectures corresponding to deep neural networks that is making it all work. So we better kind of understand why they need to be deep, and don't dismiss that side. And the structured data, that's kind of the one that is probably dismissed the most often, because most often you don't want to assume anything data. But at the same time, it is known in theory of computation complexity in computer science that if you don't want to assume anything about the data, it means that you are considering the worst case possible data that some adversary gave to you. Then we know that algorithmically training even very simple neural networks is NP complete. It means that everybody in computer science believes that there is no fast, efficient algorithm that would do it for worst case data. So there is some in the structure of the data on which we are interested to apply these networks that makes it work. So we cannot dismiss that side, because if we dismiss it, we will not understand why on the data we are interested in it is working. So the kind of maybe a bit controversial slide, but nevertheless, is this one, that the kind of branches of, say, mathematics, computer science, and statistics that study learning, they look at the problem, each of them from one side. So learning theory and approximation theory would be looking at the function, whether the function is good enough. And optimization theory and large part of computer science is looking at the algorithm, whether it's efficient algorithmically, and dismissing the other two. And then there will be, say, signal processing and part of statistics and part of information theory that would be very good at describing with some kind of Fourier transform and wavelets and tools like that how the data are structured, but not really caring about whether that helps you or hurts you in learning the data. So people really need to come back together and form like one science to understand how deep learning works. And so this is a point where in this talk the physics will come in, but maybe it's also a good point to make this a bit more interactive. If somebody has some questions on the first part, then you could ask them. And if not, okay, or if you ask them via some chat and they will ask them to me later, then I will go on to the.
I don't see the question on the slide though, but if I can ask, like, how much do you believe that like the current all these three parts are perfect? Because like I'm still kind of fascinated that if you like really look deeper into the PyTorch and TensorFlow code, you can find like the easy bugs. Like just if you look on the Fast AI version 2 course, they were just like trying to re-implement neural network from the scratch, and then they compare to the PyTorch code and they see, oh, why is like divided by square root of 5 here? That seems like a bug, and it really was a bug, and they were able, like, and this is the code that like you know, thousands of people are using every day. It was for some like random
Yeah,
reason.
so that's an interesting point. So there are, you know, plus and minus. So as you're saying, I mean, they are for sure far from perfect, but they're, you know, not kind of part of the magic of why it works so well, that it's really robust. That even if you make a bug, it's not so bad, right? You still do well on your test set. So that's what you need. I mean, for work, you need it to be robust. So this is kind of just, you know, a kind of adversarial case for the developers, because it's so robust that it's making it really hard to search for those bugs that, you know, they don't show up unless you really like dig into it very, very deeply. So yeah, that's a good point. From my point of view, like how close to kind of some optimal you are, I mean, I really don't know. Like on the algorithm side, I'm pretty sure that we are doing that, one can do much better. The question is, can you do much better and still keep it so scalable and so robust as the gradient descent is? So that's not so clear. But I will probably not get there. But in some of our works, we are showing that the gradient descent is highly suboptimal if you actually give it, you know, simpler models and more computational power. But the algorithms that we are showing are better, are less robust, and maybe more and much more sensitive to the assumptions, you know, to these kind of little bugs would completely destroy some of the other algorithms and just still keep the stochastic gradient descent kind of doing its job. So these are that's a very good question, but I don't think anybody has an answer to this as of today. So let me go to the physics. So as I was saying here, there are kind of two. So I'm physicist by background, so that's kind of my job. So I give here 2 points. Kind of one is the first one about the models is kind of more philosophical, like how we approach the problem, and the second about the methods is very concrete, and I will explain kind of how that enters in a few slides. So first about the models. So that's the slide that is probably the most kind of philosophical, is just to explain kind of what the word of model means in physics and what it means, say, in machine learning or in general in data science. And in machine learning, you call model basically the neural network. You assume that your model is really something faithful enough that it can really capture all the properties of your data, that you can fit your data, that you can really describe your system. So in physics, we would not call this a model. We would call this maybe an ansatz. It's kind of a word, you know, that's something that really describes well, faithfully the world. In physics, model is something more abstract. Is actually something that, you know, does not aim to describe all the details. On the contrary, it aims to forget most of the details, all of those that are kind of not key to capture the essence of the problem. When you want to explain some properties, so for instance, the one, why doesn't overfitting hurt? You want to get rid of everything else except what is really needed to explain that property. And I just give here the example of the Ising model. I'm of, by no means, you find on arXiv people explaining pretty much everything with the model. So I'm not saying that Ising model will explain deep learning, but just to give you the example of how models are used in physics, right? So everybody in physics agrees that this Ising model is a good model to explain magnetism, to explain the very fact why magnets at low temperature behave like magnets, and if you heat them up, they don't behave like magnets anymore. And this model, here it is kind of sketched. It doesn't include quantum mechanics. It doesn't include any particular detail of any particular magnetic material. It doesn't include anything about molecules. Even Maxwell equations are not there. Nothing of this physics that you would imagine you need to describe magnetism. Yet, we agree that it captures kind of this phase transition from the paramagnet to the ferromagnet or vice versa. And having models of this type that are not describing all the detail but are capturing the essence, this is something in which physics is very good. And in a system that is complex, where you have so many elements that you just cannot include them all, you kind of need a bit more of these spherical cows in the vacuum to kind of understand and proceed what's going on in the theory. But that's kind of the way you approach it. I will come to the methods later that kind of give a more strong mathematical point. So what would be such a model for a neural network? So I said the Ising model is not a good one. Don't misunderstand me. One model that I like a lot, that I think is very useful to study as a kind of toy model for neural networks, is this teacher-student neural network. So what you do here, so in the simplest version of this model, you take your input data, so X, as IID noise, so just random noise. So not only the samples are independent from each other, but also each of the pixels is kind of independent from the other pixels. So this is no way describing any images. This is just noise. Then you take a neural network that you pick as you want, that will be called a teacher neural network. You set the weights in some way that you know, this will be these W stars here, and you use that neural network to generate the labels Y. And then the student network takes the inputs, takes the outputs. To simplify your life, you can even assume it knows the architecture of the teacher neural network, but crucially, you don't give it the values of the weights W star. And kind of, if it is able to find back the W stars or something equivalent that gives you the same output, then it can learn the same function as the teacher is representing. And that's the question here. More concretely, how many samples of data do you need for the student to be able to learn the teacher with a given algorithm? So of course, it all depends, the triangle here, the algorithm needs to be there, the architecture is there, the architecture we just say postulated, and the data structure is put aside. In particular, the structure in the inputs X is put aside, but there is still some structure in the correlation between the X and the Y, the labels and the inputs. So this is a model. In physics, people kind of started to study that model for studying neural networks a long time ago. So actually, this is one of the first papers in '89. So whatever, 30 years ago. And this is some journal of physics A. They started with kind of the simplest neural network where you don't even have any hidden units. So this is just the generalized linear regression as I described it. And here I call it the teacher-student perceptron. Perceptron is how it's called in physics. So you start with the weights W star, that here they will be drawn at random from some distribution, and the teacher network creates the labels, and then from the inputs and the labels, you try to learn the function. And kind of what is interesting here, that the physicists started to study that. And in physics, we always have some kind of thermodynamic limit. The system has many particles and we send that number to infinity. So that kind of thermodynamic limit here corresponded to the case where the number of samples n goes to infinity. The dimension of the input space also goes to infinity, that's p, and the ratio is constant. So that's kind of, for a physicist, a very natural limit in this case. From a point of view of a mathematician or a statistician, of somebody working in learning theory, this is already really challenging, because statistics was for, say, 30 years to something like 2010 or maybe 2000, depends who, working in the low dimensional regime, where the dimension p is fixed and the number of samples n goes to infinity. So remember fitting the line, there were 2 parameters you are learning and you have many points. So p is 2 and n is growing large. And if you have number of samples that is just comparable to the number of parameters, that's the high dimensional regime where a lot of the math used in statistics just goes away. Not powerful enough to give you non-trivial results. And this is where the methods of physics come in, because back then, these same people, they were also studying physics of disordered systems, and there we actually do have a method, developed methods 40 years ago, that are able to deal mathematically with this high dimensional limit. And this is called the replica method. And so they just took this mathematical method and applied it to this problem. And they were able to, for instance, draw a curve that is here on the graph. That is, how does the test error in this simple model depend on the number of samples divided by the dimension? So there's this alpha parameter. And you see that it has a peculiar behavior. It doesn't go down kind of smoothly, but it actually, first it goes down kind of as if you would expect. The more samples, the smaller will be the test error. But then suddenly, at some point, which is 1.24, it drops sharply to 0, and then it stays 0. And this is in particular when the teacher weights are plus minus 1s. That's a particular case where it looks like that. So you know, these are physicists. They go, oh, there is a first order phase transition. If you look at the title of the paper, there is a first order phase transition in this learning problem. So kind of what's mathematically interesting here is that this replica method, you know, if you're a rigorous statistician, you cannot really write a proof. There are some assumptions that kind of in theoretical physics go through, but if you're a mathematician, you're stuck there, and the proof doesn't go through. And already an interesting mathematical problem that was open since these, you know, 1990, to prove that this formula they derived is actually the right formula, really, with all the epsilons and deltas. And this was an open problem for 30 years, you know, until kind of, you know, our actually look back at this problem. And with the development in math and in, you know, computer science and statistics in the past, say, 20 years, we actually managed to prove that this is the right formula, and kind of on the way developed a nice piece of math and generalized to generic activation functions and priors of the teacher, and have also algorithmic interpretation of all that. But I promised some more of the physics, so now maybe I'm a bit jumping forward in my slides. Why is it not going forward? Yeah.
Looks good from my side.
So before that mess, I was telling you about the phase transition in the learning problem, in the simple one. And so I kind of wanted to remind you what you know about phase transitions from, again, back in the high school from your physics, right? So I hope all of you at some point at your school, you have seen a diagram like that describing the phase transition in water. You have the ice and water vapor, and there is a critical point. If you are at high pressure and big temperature, then water would turn into vapor without a phase transition, actually. This, oh, I see my mouth, so I say cancel. No, what's going on? Okay. I don't know. But the slides are still working, so I will just try to ignore it and continue. So this slide is showing you a pretty peculiar phase of water. But now I don't know whether the video is working. Yeah, maybe it's working. The video is not working. So I get you are not seeing a video, right? Are you?
We see the slides. We don't.
Oh, I'm not.
You're frozen as a person.
I could just tell you about the phase transitions without the slides, I guess.
Yeah, well, that's also a possibility.
Let's forget the slides. I know my slides. So there is this fantastic thing called metastability with that you can try at home with the supercooled water. So you just take a bottle of water and you put it into the freezer. But be careful that it's distilled water or some kind of clean water. And if you do it right, it will actually stay water, say, down to maybe -5 degrees Celsius. And then that was what the video was. Maybe Flo will fix it on the other computer, right? But before he does that, you will see that by basically a small just like hit into the bottle, the water will suddenly freeze. That it was, you know, already at -5 degrees Celsius as a super cool liquid, but it will become suddenly ice. So you usually don't see that. Like another striking example of this metastability is actually a diamond. So diamond is actually at normal pressure and normal temperature a material that should not, you know, it's not at its thermodynamic equilibrium. If it actually suddenly turned into carbon, you know, graphite, something very ugly and uninteresting, it would have a lower energy, and by turning into graphite it would actually release energy. Nevertheless, it keeps its metastable nature as a diamond, luckily for, you know, all of us or you who have a diamond ring or anything like that. And this peculiar notion of metastability that comes in nature with these first order phase transitions. First order here refers to the fact that, say, the density of the water changes sharply at the phase transition, or of the ice changes sharply. So this phase transition that I have shown you for the binary perceptron problem is also first order. The test error was dropping sharply. So if this happens in nature, this also happens in machine learning, and is associated to an algorithmic hardness. For the same reason that the physical dynamics that is kind of governing the properties and the physical properties of diamond doesn't let it turn into graphite, but keeps it to be a diamond. For the same reasons, the algorithms can get stuck at bad test error and not find the low test error. But you see that here it works the other way around. While with diamond, we are happy it stays diamond. With the test error, we are not happy if it actually does not become low and keeps being high. So that's an interesting concept that analyzing these simple models can actually reveal in machine learning, that there are these phases where if we had an exponential costly algorithm that would be able to explore all configurations, then we could find good test error, but with the kind of efficient and polynomial algorithms, we are not able to do that.
Can you ask them if I can share my slide?
Share your somewhere. Yes. So this is what I described to you, that experiment that you could do. Oh, but I see. But is this still this camera? This is very confusing. So that's the experiment with the water. And here is the slide with the diamond. And yeah, and this is kind of explaining the analogy between the algorithmic hardness in pretty much any algorithmic problem. If you encounter in some high dimensional limit this first order phase transition, then there is an associated algorithmically hard phase that corresponds to the physically super good liquid that you might be familiar with from kind of physics or your general kind of culture. And here I was giving kind of a dictionary that this replica method, that gave us by some magic formula that then for 30 years was kind of mathematically open why that is the right formula, actually is a kind of a general mathematical method that if you, instead of positions of molecules, think of the weights in the neural network, and instead of interactions between molecules, you think about the input data and the labels that plays the role of the interactions. And in terms of the inverse temperature in physics, you take the number of samples per dimension. And in terms of the physical dynamics, you think of the algorithm. And in terms of, say, the magnetization or the density, you think of the test error. It mathematically really is just a dictionary from one another, but otherwise it works the same. So these methods that people have been developing for 40 years to understand physics of materials such as glasses and diamonds and things, disordered materials like that, they can readily be applied in machine learning or in computer science. And kind of what they have that the traditional methods in probability, statistics, computer science do not have is kind of that they overcome the difficulty of the high dimension. Because when you write probability distributions in high dimensions, then things become mathematically very scary. But in physics, we kind of dealt with the high dimensions since the beginning because the number of molecules corresponded to the dimension in this dictionary. And that was always 10 to the 23 or something like that. So that's the very, we need to start in that limit to say something meaningful about physics. And so somehow, luckily for people in statistical physics, this is also the limit or the regime in which kind of the machine learning and inference and statistics in the past 10 or 20 years are living. So we are just a little bit ahead in the development of the right mathematical methods in physics because we were just thinking about this limit from very early on. And that will be kind of concluding one part of the talk, but now we had so many breaks that I will not be asking for questions and rather concluding that so far described, told you about this teacher-student model and described a very simple case with no hidden units. And some interesting, methods, how we can mathematically deal with that even are not obvious in statistics, and algorithmic consequences it might have in relation to physics. But the question you should be asking is, this is not bringing us towards the theory of deep learning, because there were not even any hidden units, not speaking, say, 1,000 hidden layers. So that's correct. So let me put it back on my triangle. And so what I so far described was on the architecture side, no hidden units. The algorithm, I didn't really mention it, but I was not really describing the gradient descent, but rather some kind of more fancier message passing algorithms, that I was kind of mentioning, answering Peter's question, that they are not so robust and universal as the gradient descent, but they sometimes work much better on the simple models. And the structure in the data, there was no structure, right? I just started with, the input was IID noise, so no pictures, nothing whatsoever. So we would want to go to something more realistic, right? And so multiple wide layers and the gradient descent based algorithms as everybody is using them, and interesting structure data, understanding how the structure is actually influencing the fact whether or not we can learn efficiently. And so this is what we are, but it's time to conclude, at least in this talk. So each of these three directions, this is basically everyday occupation of my group. And this is examples, kind of highlights of our past papers that I like, where we kind of advance the state of the art on these three directions, but kind of keeping in mind all three of them. So this is something that I like to stress, and that many of the works that you see out there that have, that end up with maybe big impact or are very interesting, but there are really not so many of them that deal with the three at the same time. You can kind of, now that you know about it, you can like check your favorite papers and you realize, oh, these are just not at all considering the algorithms, or oh, these are not at all considering the generalization error. So we try to keep the three of them in mind, and you see that these papers go in some of the top machine learning conferences. So we are pretty kind of known, and this work is kind of on the top of what the theory of machine learning is doing today. And so here is back just the triangle. And if I had more time, or if there were less practical problems, then I actually have like a little 10-minute part about each of the directions and how we are kind of proceeding towards the green from the blue. And these blue here only, that we can deal with only a few hidden units, but we can deal with hidden units and have some interesting results there. And we can describe what gradient descent is doing in high dimensional non-convex setting, kind of in cases where like nobody else could, and putting some interesting structure into the data so that some properties that we observe, say on the CIFAR on MNIST, really get nicely reproduced by that hidden manifold model. Or if you want to ask about that, or if you go to those papers, actually that's what you will learn about. But otherwise I will stop here, not to go like too much over time.
Okay, sorry, I was just writing the question to Slido. That was really interesting. I have to say that like it's kind of fascinating. It slightly reminds me like 20 years ago there was the big inspiration of the theoretical algebra, like really the Grabner basis and things like that for the mathematical statistics, and like this sounds like this could be something like physics for the machine learning. We have many questions.
Yes, so I just need to move the window. Okay, should I start from the first one? In the first order transition phase diagram, it suggests alpha bigger than 1, which means number of samples bigger than number of dimension. But most cases are dimension much bigger than n, right? Yes, so if you really go to deep learning, you do often have many more parameters than number of samples. This is right. But if you stay in this simple case of linear regression without hidden units, then the number of parameters and the input dimension is the same thing. So this is not the same thing in a neural network with hidden units, but in the linear regression is the same thing. And so you don't have the distinction between the dimension and the number of parameters. And in that case, this regime around alpha 1 is kind of where the interesting things happen. If you had much more parameters than number of samples, then it means also your dimension would be much bigger than the number of samples, and then you just cannot learn anything because the teacher used number of parameters that is the dimension. So that's just a particularity. If you go back to linear regression, this is what you need to look at. I didn't fully understand the idea that the ability to fit random labels, if we have enough parameters, implies that many theoretical concepts are useless. So that depends whether you know or not about the Rademacher complexity-based bounds. So this is basically the kind of flagship concept in theory of learning. And if you actually look at the definition of the Rademacher complexity and what these bounds are actually saying, you understand directly that it is linked to the ability of the neural network to fit random labels. And if a network is able to fit random labels, then these Rademacher complexity-based bounds are completely void. They are just telling you the generalization error is smaller than something big. And so it's not useful. So, okay, I hope that answers the question. If not, like Google, generalization bounds based on Rademacher complexity, or go to the paper, that should be clear. So Jan Bogar, what is the motivation, except curiosity, for physicists to start looking into theory of neural network? They are very different from most mathematical models in physics. So, so let me translate it. What is the motivation, except curiosity, for physicists to start looking into the origins of the universe? Yeah, I think I could ask the question the same way. Yeah, is the curiosity. Is the curiosity, and is the fact that, we can understand something that nobody else understood before, and so we do it. And that's just, for me, that's the main motivation to the research. A part of the fact that, then you get invited to famous places and people say how smart you are and give you some prizes. So of course, some of us are also motivated by these kind of, things. But the primary motivation is the curiosity. So whether there is something behind, other than curiosity, or the mere fact that you can say something about an interesting system that nobody before could, and you're kind of moving that frontier of knowledge. Maybe others have other motivation, I don't. Please finish the presentation. We have 10 minutes left. Okay, thank you. Jan, I think I can give my 2 cents on your question. The thing is, neural network is not very different from the physical mathematical problems physicists deal with. Yeah, that's what I was kind of trying to give you in the dictionary, right? That if you just translate the terms, you end up with a mathematical structure that is very much related. I didn't say the term in the talk, but spin glasses would be kind of a generalization of the Ising model, where not all the interactions between the little magnets are the same, but they are kind of random numbers. So that has a very interesting behavior. And the methods developed to study these spin glasses are this replica method, and the methods are kind of the same. And from the, if I could say that the neural network is a type of spin glass, of course that's like moderately interesting if you want to understand neural network, just to say that. But yeah, it is very much similar to that. Are you familiar with work on theory of deep learning by Naftali Tishby, the information bottleneck approach? If so, can you share your thoughts, take on it? So yes, I am. I mean, Naftali Tishby turns up to be one of the physicists that worked on neural networks back in the 90s, and I don't have like his paper cited in this particular seminar, but I could. Like, he was one of the ones that back in the 90s was applying the replica methods to the spin glasses and to the neural networks and writing reviews about that. But that's of course not what you meant in that question, because that work of his that is very interesting, very valuable, but very little known. You are referring to the information bottleneck. That is an interesting concept, kind of related to what people study in information theory and error correcting codes. So there is some interesting idea in that, right? That basically the neural network tries to kind of tries to find a sweet spot in terms of the mutual information between the input and some layer and a layer and the output. So we actually do have a paper in NeurIPS 2 years back, about estimating this mutual information in a tractable way, because he kind of does the theory for a property that is even hard to compute. So if you cannot even compute it in simulations, how do you check whether the theory is correct or not? So we found a way in some specific setting to compute it very tractably on huge neural networks. And once we had that method to compute it, so that's, that's shared on GitHub, you can have a look at it. We tested kind of the claims of the theory, and we could see some properties he was saying should be happening in some cases and not in the others, and couldn't kind of conclude really whether, what is true and what is not true. So, I mean, if you're interested in more details, I could give you more details, but I guess that should do for the answer. Next question, Jakub Vrabel. Thank you. Concepts from physics, free energy, variational inference, renormalization group play a crucial role in machine learning. What will be the next big weapon from physics? Yeah, I cannot predict the future. I would say, whatever my group is working on, just because that's what I want it to be and that's what motivates my everyday work. But other than that, that's a good question. There is a lot of serendipity in science, right? When I look back at basically my most successful papers and most well-known papers, basically the result there, it's not that we kind of planned for it. It just came kind of randomly. There was something interesting happening, and when we digged into it, we realized, oh, but this is really interesting and nobody knows. And so this concept of serendipity doesn't cease to fascinate me in science, how things kind of come out of nothing. So things are really hard to predict, at least in kind of fundamental theoretical research. So the next question, Jan, the equation of neural network is actually some linear transformation, which is very similar to all other physical problems. That's not a question, but is that true? I mean, the neural networks, the crucial difficult thing there is the activation functions that are nonlinear. There is a really nice line of research by Andrew Saclay that I mentioned, Surya Ganguly, a couple of colleagues, where all the activations are actually linear, in which case the approximability of those functions is very limited. It's all just linear algebra. But then we can understand quite nice things about the dynamics, about the learning dynamics. So that's an interesting case, but it's not linear. And in physics also things are not often linear. So I would not much agree with that claim. The next question, could you recommend a book on statistical physics and replica cavity method in particular for somebody with math background, no physics background? So there is a book by Mézard and Montanari from 2009 called something with I can give the reference to the organizers and they can share it. If you type Mézard Montanari in Google Scholar, it's cited I don't know how many thousand times. You should find it. That's a nice book with for people, it doesn't assume any of the physics. It does a little introduction to like what statistical physics is, but it's written pretty much for people with some basic kind of background in math and computer science. Some basic notions of combinatorial structures and data structures. So ask me more by email if you're interested to read about these things. I will be happy to send you references. Phase diagram suggested a phase transition when n increases. Does this imply similar phase transition on test error can happen on deep learning when we feed in more data? Yeah, absolutely. I would rather say when we feed in less data, right? Because most of the examples we kind of have in mind are kind of these databases where for the number of examples that you have there, things are kind of working. And so they will just be working a bit better, but nothing drastic will happen if you put more data, at least say if I think of ImageNet or CyFAR on MNIST. But if we go to smaller number of data, then of course the test error, if you give it fewer samples, then of course the test error is growing. So now you will not see anything as sharp as you have seen in my figures, because for instance, in MNIST, the input dimension is something like 700. And you really need this number to be much bigger to see that sharp drop. So so because of the fact that the dimension is still, is big but finite, you will not see as sharp drops, but we definitely see some, similar types of behavior in deep learning when we train on some of these classical data sets, but not as clear as it was in my figures. But kind of the consequences of the phase transition, for instance, the fact that if there is such phase transition, then it is making the job for the gradient descent harder. That is something that we hypothesize translates to deep learning. And basically the kind of implementation tricks that people are using to make gradient descent work better are maybe fundamentally many of them are there to exactly mitigate kind of this the consequences of this coming phase transition if the system was bigger. So that's kind of one of the hypotheses with which we are working and kind of showing things in that direction.